Now we're back. Let's talk about mixed strategy Nash equilibrium. Um, to begin with, let's talk about what a mixed strategy even means. So remember a game like this? You can choose to play B or you can choose to play S. What if you mix between the two? So you play B two-thirds of the time and S one-third of the time. That would be a mixed strategy, right? So a mixed strategy is a probability distribution over pure strategies. So it's a probability distribution over all of the actions that you have available to you. Um, every pure strategy is also a mixed strategy. So mixing with a probability 1 and a probability 0, that's just the same thing as choosing B. And so every pure strategy can be represented as a mixed strategy. Uh, But allowing for mixes just allows for a lot more flexibility when you're considering these types of games. Okay. Um, the next, I'm going to be more specific about this in a moment. The first thing I want you to realize is that as soon as you start mixing over actions, now your payoffs aren't guaranteed, right? You're not guaranteed a particular number. So now we have to make one additional assumption about players' preferences, which is risk neutrality. It's a very simple assumption. It's just that your payoff is now your expected payoff. Um, and so a lottery is just any situation in which the payoff is uncertain. Right? So an actual lottery is also a lottery. Um, but so is attending class, right? It might make perfect sense. It might be fun. Or it might be a completely dull affair where nothing happens and you're bored out of your mind. Um, that's a lottery. Going and seeing a Marvel movie, that's a lottery. Some of them are pretty good, some of them are pretty bad. Um, so lots of situations in life can be represented as a lottery. Risk neutrality just means that the payoff is the same as the expected payoff. So what you care about is the expected utility. If, for instance, if we have a lottery, let's call it L1, which generates a utility of 1 with probability 0.5 and the utility of 10 with probability 0.1 and the utility of 0 with probability 0.4, then my expected utility from the lottery L1, if I am risk neutral, will be 0.5 times 1 plus 0.1 times 10 plus 0.4 times 0, right? So pretty simple. So that's just 1.5. Okay. And so if you're risk neutral, you'd be just indifferent between getting the lottery L1 and just being offered 1.5 units of utility for sure. If you're risk loving, then you prefer having the uncertainty of maybe getting 10. That seems appealing to you. People who play the lottery are risk loving. If you're risk loving, then your um, utility from L1 will be greater than the expected utility of the different. Let me just call this. Let me just call this 1.5. And if you're risk averse, then your utility from L1 will be less than 1.5. right? Then you'd rather have 1.5 for sure instead of this lottery, which might give you 10 or might even give you nothing. Okay. So that is how we evaluate payoffs when we have uncertainty. We're going to assume risk neutrality here. Um, we can do a lot more when we assume different types of utility risk aversion and risk loving preferences. Um, but this is an undergrad game theory course, so we'll assume risk neutrality. Okay, now let's talk about a mixed strategy. So alpha 1 is a, let's call it alpha I. It's a particular mix over or a particular probability distribution over elements in capital AI. Right, so do you remember AI, small AI? That was an action chosen by a player when we were thinking about pure strategy Nash equilibria. Now that we're thinking about mixed strategy Nash equilibria, a particular action, right, the choice that a player makes here is going to be a probability distribution over all of the elements in the action set, right? And so that alpha I will come from delta AI, where this whole delta AI is the set of all possible probability distributions over elements in AI, right? So the delta, capital delta AI is the set of all possible probability distributions. So any probability distribution that's possible over the elements of AI, that's contained in delta AI. Okay, and finally, um, alpha will be just the set alpha 1, alpha 2, up to alpha n. This is the mixed strategy profile. So this alpha without the subscript specifies the mix chosen by player 1, the particular mix over all actions chosen by player 2, player 3, so on. Alpha I is for a particular player I. Alpha minus I specifies the same thing for all players other than player I. And alpha star is a profile of mixed strategies. Is a mixed strategy Nash equilibrium if and only if the utility, uh, the expected utility that player I gets from choosing alpha I star when other players choose alpha minus I star is at least as large as the expected utility that player I gets from choosing alpha I prime. Other players choose alpha minus I star for all I. Right, if this holds true for all players I, so actually, first I have to cycle through all of the alpha primes. I have to check for every possible value that this alpha I prime could take. So let me write that out first. For all alpha I prime in delta AI and for all. Okay. This is a definition for mixed strategy Nash equilibrium. It's very similar to our earlier definition of a pure strategy Nash equilibrium. Um, Tell you what, I'll write that down in a second. So this is a pure strategy Nash equilibrium definition. So A star is a Nash equilibrium in pure strategies if and only if the utility that player I gets from choosing a I star given A minus I star is at least as large as the utility that I gets from choosing AI prime A minus I star for all AI in AI for all I. If you look at the differences, first difference is that we didn't used to have that expected value. We now need the expected value because we're talking about situations in which the payoff is uncertain because players are mixing over actions. And then the rest of it is just using alphas instead of A's. And then the alpha has to come from this set, the delta of AI, which is the probability distribution, the set of all possible probability distributions over actions, whereas the action just came simply from the action set. Okay? But otherwise, the idea is exactly the same, that you have an equilibrium where you have stability, right? No player should be able to unilaterally do any better um, than they currently are under the equilibrium mixed strategy profile. Um, and if that's true for all players, then you have stability because nobody hasn't the incentive to move away from the current mixed strategy profile. Okay. Another way of writing the same thing is just like we had earlier, alpha I star should belong to B, the best response of I, alpha minus I star for all I. Okay. In order for alpha star to be a mixed strategy Nash equilibrium. Okay. And the best response is defined the same way as we had earlier. So um, we find the mix over all possible actions that maximizes player I's utility. So the best response, as before, is defined for a player I and given alpha minus I. Okay. Um, BRI as a function of alpha minus I will be the set that contains all alpha i's such that the utility that player I gets in expectation from choosing alpha I given alpha minus I should be at least as large as the utility that, again, I also have to get used to writing expected utility now. The expected utility that player I gets from alpha I prime, where the prime just denotes a different um, action, a different mix over actions, alpha minus I, for all alpha I prime in A delta AI. Okay, so best response for player I, just in plain English, it's always going to be a function of the choices made by the other players in the game. So that alpha minus I, you take that as a given. So you take as given how other players are mixing over their actions. And then what you're finding is this set of alpha i's such that player i's utility is maximized, taking as given this alpha minus I. Okay, this is the same alpha minus I that we uh, put into this in as the input that we used as the input into this function. Okay, so get rid of those a little bit, make it a little neater, and check over all alpha I primes. That check just simply means that you want to make sure that this is actually the best thing that player I can do. So you're looking over all of the possible options available to player I. All right, let's give this a pause for now. So this has been a pretty definition heavy uh, video. In the next video, what we'll do is an example. So we'll think about how to find a pure and mixed strategy Nash equilibria when you have a 2 by 2 matrix.